Hello everyone, in this video we are going to study fully connected network versus convolutional neural network. It is an important topic in deep learning. Also we will explore two foundational neural network architectures. First we will see fully connected network architecture. In that first one, dense connections. In an FCN, every neuron in one layer is connected to every neuron in the next. This forms a dense web of connections which allows the network to learn complex patterns. But it also means there are a lot of weights to learn, which can be computationally expensive. Second one is input flattening. Before data enters an FCM, it's converted into a single long vector. This process called flattening loses or spatial for or positional relationships. For example, in images, the positions of pixels are important, but FCMs treat all the inputs as just a number in a list. Third one is eye parameters. Since every neuron is connected to every other neuron in the next layer, FCN have a very high number of parameters. This can lead to overfitting, especially when we have a small data set. The model memorizes rather than learns. FCN, also called multi-layer perceptrons, are useful when the position of input data isn't very important, like in tabular data, but they are less efficient for images or signals where structure matters. Next, we are see FCN operations and characteristics. First one is global patterns. FCNs are great at learning global patterns in data, but they don't capture spatial relationships which are important in images. For example, they would recognize that two nearby pixels in an image from an edges or a shape. Second one is high cost. FCN require a lot of computation, especially with large inputs like images. This is because of the large number of parameters and connections. As a result, they can be costly and slow, limiting their use in some real-world applications. Third one is tabular data. FCMs works well with structured data like spreadsheet or time series. They are also used in some NLP tasks, but they are less effective for tasks that need spatial awareness like image processing. While FCM perform well in simple tasks like digit classification, they struggle with high resolution images because they don't understand spatial structure, which is where convolutional neural network come in. Now we will see convolutional neural network architecture. First one is convolutional layers. These are the core of CNNs. They scan the input using small filter to detect features such as edges, corners and textures. This helps CNN understand visual pattern in images. Second one is pooling layers. This layer reduces the size of the data, which speeds up processing. At the same time, they keep the important features, making the model more efficient. Third one is spatial hierarchy. A CNN preserves the spatial structure of the input, meaning they know which features appears where in an image. This is very important in tasks like images recognition, where the position of features matters. CNN are efficient because the same filters are used across the whole image. Famous CNN models include AlexNet, VGGNet, and ResNet, which are widely used in computer vision tasks. Next, we will see CNN operations and characteristics. First one is spatial learning. CNN are great at learning spatial features, understanding the structure and layout of images. This helps in tasks like recognizing objects or detecting patterns. Second one is parameter sharing. Instead of using separate parameters for every part of the image, CNN reuse filters. This makes the network simpler and faster and reduce the number of parameters. Third one is noise reduction. Using technique like max pooling, CNN ignores small disturbance in images. This helps the model become more robust and reliable. Last one is broad applications. CNN are widely used in images, videos, and even audio. They often need less processing, making them user friendly for real world tasks. From object detection to image segmentation, CNN are powerful tools for visual tasks because they naturally understand spatial data. Next, we will see key difference parameter count. First, FCN fully connected network, quadratic growth. FCNs have parameters that increases quadratically with input size. This means that as input grows, the model size explodes quickly, becoming too large to handle. For example, using FCN on high resolutions images like ImageNet would result in billions of parameters, which is computationally impractical. Next, CNN, convolutional neural networks, linear growth. CNN are much more efficient, their parameters grow linearly with input size. This allows CNN to handle large input like HD images and videos without becoming too heavy. This makes CNN scalable and suitable for real world application. The bar graph visually shows the huge difference. FCN have much higher parameters count compared to CNN for the same input. This highlights why CNN are preferred for image processing tasks. Next, strength of CNN. First one, automatic filters. CNN uses convolutional filters that learns features directly from the data. Manual design needed. These filters detect crucial details like edges, textures, and shapes, which are essential for understanding images. Second one is simplified maps. Pulling layers reduce the dimensionality of the data. This creates simplified features maps, preserving the important parts while discarding noise or redundant info. It helps reduce computational without losing key features. Third one is complex patterns. CNN can learn complex abstract patterns while using fewer parameters. This makes them very efficient and powerful, especially for deep learning tasks. The ability to automatically learn and simplify features is a core strength of CNN. This also supports transfer learning using predefined models, making CNN versatile across various tasks. Next, we will see weaknesses of FCN's scalability. First, poor scaling. FCN do not handle large input sizes well. As image resolution increases, the number of parameters grows rapidly, leading to high computational cost. This makes it inefficient for high resolution images. Second one, overfitting risk. FCN have many parameters which increases the risk of overfitting, especially when training on small datasets. They tend to memorize the training data rather than generalizing. Raw pixel data issues. FCN are less effective when processing raw pixel inputs. They flatten images which destroys spatial relationships which are crucial for image understanding. Due to these limitations, FCNs are not ideal for modern computer vision tasks. Convolutional neural networks are better alternatives as they preserve spatial features and scale better with input size. Next, hybrid approaches. CNN for features. CNN are excellent at extracting robust features from raw image data. They preserve spatial relationship and excel at pattern recognition. This step is a crucial because it transfers raw pixel into meaningful feature maps. FCN for classification. Once CNN extract high-level features, FCN take over of the classification task. FCNs are used to learn complex relationships and make final predictions based on the extracted features. Combined power. This combination leverages the strength of both models. CNN for their efficient features extraction, FCN for their powerful classification abilities. The result is a more powerful and flexible model. As mentioned at the bottom, hybrid models like region-based CNNs offer enhanced performance by using CNNs for feature extraction and FCN for classification. Last one is conclusion, choosing the right architecture. First, data nature. Understand your data first. It is a high dimensional with spatial information or is it low dimensional? FCN work well for simple structured data while CNN handle complex spatial data effectively. Scalability. CNN are preferred when scalability and efficient features extraction are needed. They are especially ideal for image-heavy applications because they preserve spatial features and are computationally efficient. Hybrid model, sometimes using both CNN and FCN together, can be the best approach. Hybrid models combine the strength of both CNN's extract features and FCN perform classification. This provides flexibility and power suitable for advanced applications. Choose the architecture based on the complexity and type of your data. Use FCN for simple low-dimensional inputs. Use CNN for complex image-based or spatial data. Thank you.